Hey folks, my name is Nathan Johnson. Welcome to lecture 4 of vector calculus, which is all about the arc length of a path. So what we're looking at today is, well, remember we've talked about paths and curves so far, and remember a path, it's sort of like a particle moving around a curve, and what the arc length of that path is just how far did that particle move, okay? In other words, how long is the curve? If I think of the curve as a piece of string that's bent and wavy and curving around in n-dimensional space, what is the length of that piece of string? In other words, if I was to pull it taut so that it's now just a straight line, how long would that straight line be? That's what the arc length is. Okay, so how do we compute this? And in this video, we're going to spend quite a bit of time trying to come up with a formula for this quantity here, okay? We're going to try to drive it fairly rigorously, and that's going to take us quite a bit, but then we will do some numerical examples, actually making use of the formula that we come up with towards the end of the video, okay? So that's where we're going. Let's start off with how do we come up with a formula for this? And actually, even more basic than that, how do we come up with a formula for estimating this? If I just wanted to estimate this quantity, this curvy length here, how would I do that? Okay, and sort of the maybe first thing that I would try is, well, let's estimate it based in terms of things that I already know how to compute, which basically are straight lines, right? If I have a straight line segment and I want to compute the length of that, well, I know how to do that. Okay, so how about we take this curvy thing that we would like to compute the length of, and instead of computing its length exactly, because I don't know how to do that yet, let's draw a bunch of straight lines that are kind of close to that curve and compute the length of all of those and then add them up, okay? And sort of geometrically, it seems kind of believable that, as long as we choose enough straight line segments, then this would probably give us a reasonably good estimate of the length of the curve. Okay, so let's try to pin this down, actually write down some math that sort of quantifies this idea here. Okay, so what we're going to do is we're going to take this interval a, b, in other words, we're going to take the domain of the function, and I'm going to chop it up into m subintervals. Okay, so I'm going to say that t0, that's the left endpoint, that's a. Tm, that's the right endpoint, that's B, and then I'm going to choose m minus 1 points in between. I'm going to choose some t1, some t2, all the way up to tm minus 1. I'm going to chop that interval AB at those points. And when I do that, I'm going to have m subintervals now. I'm going to have the interval from t0 to t1, from t1 to t2, and so on, okay? And what I'm going to do is I'm just going to construct a straight line segment between the endpoints of each of those subintervals. In other words, I'm going to plug t0 and t1 into my path f, and I'm going to compute the straight line distance between f of t0 and f of t1. And then I do the same thing with t1 and t2. I plug both of those into my path f, and I compute the straight line distance between those 2 points now. And I do that for all m subintervals, and then I add up those m different straight line distances. And I kind of hope that as long as m is big enough, this sum of straight line distances should be a reasonably good estimate of the actual arc length of that curve. And sort of geometrically, this seems reasonable, right? It seems like if I take m to be bigger and bigger and bigger and bigger, so my line segments are all getting smaller and smaller and smaller, they're getting closer to the curve, it seems like I should get a reasonably good estimate of the arc length, eventually, as long as m is sufficiently large. So let's actually try to compute this, okay? Let's come up with a formula for this sum of straight line distances, okay? And so what I'm going to do is I'm going to notice that, okay, on the ith subinterval, in other words, between the 2 points f of ti and f of ti minus 1, okay, so that interval from ti minus 1 to ti, okay, what is the straight line distance there? Well, I know a formula for computing the length or the distance between those 2 points. Okay, in n dimensions, you just do the Pythagorean thing, but with more sums of squares, depending on how many dimensions you're in. Okay, so you just do, what is the first entry of this vector here? Okay, well, we're going to call it delta f1 of ti, right? Okay, and all that means is, well, the first coordinate function of f with ti plugged into it, minus the first coordinate function of f with ti minus 1 plugged into it, okay? In other words, it's the difference of the first coordinates, on that ith subinterval. If this is a two-dimensional path, a path going into R2, like in our picture that we've been looking at, okay, then what this would be is, how far has the x coordinate changed on that ith subinterval? Okay, and then you do the same thing for f2, You've got a plus term here for f2, and then a plus term for f3, and so on up to, well, however many coordinates you have, right? If your function is going into n-dimensional space, then it has n coordinate functions, and you just do this same thing for all of them. You just measure how much that coordinate changed on the ith subinterval. You square that, and you add all these up, and then you square root the whole thing, because that's how you compute distance between 2 points in n-dimensional space. Okay, so that quantity there, this thing right here, this is the length of the ith straight line segment when we did this sort of partitioning and straight line approximation stuff here. Okay, so the arc length of the path f, it's approximately equal to, well, just the sum of these quantities, the sum of these straight line distances. Okay, so what we're going to do is, well, we're actually going to define the arc length of a path to be the sum of these, and then we take the limit as, well, basically as m goes to infinity. I would love to just say, okay, it's the limit as m goes to infinity of the sum of m of these straight line distances. But there's a slight technicality there in that I don't just need m to be going to infinity. I don't just need to chop up my interval from a to b into m subintervals and let that, go off to infinity. I also need to chop it up in such a way that each of those subintervals is getting smaller and smaller and smaller and going down to width 0. So that's how I'm going to phrase this. I'm going to say that the arc length of a path, well, it's what you get if you partition the domain AB into m subintervals, and then take the limit as the largest subinterval width goes to 0. In other words, all of those subinterval widths are going down to 0, and then you compute the limit of the sum of those straight line distances that we computed up above. Okay, so this part in here, that's exactly that straight line distance that we computed up here. And all we're doing is we're adding up all m of those, and then we're taking the limit as the widths, as the distances between the t points goes down to 0. Okay, and we're saying if this limit exists and it's independent of the particular partitioning that you're using, in other words, if it's independent of your particular choice of t1 up to tm minus 1, other than the fact that the widths have to be going to 0, then we say that the arc length is well defined and it's, well, whatever the heck this monstrous limit here is. Okay, so that's all fine and dandy. This works as a reasonably good definition of the arc length of a path. The big problem with it is how on earth do you compute it? Okay, like certainly, like I can compute this sum here just via horrendous plug and chug for particular values of m just by like computing all these things, right? Like I can plug ti's into my path, I can subtract them, I can square them, I can square root things, and then I can add them up. It's just a horrendous, tedious calculation. But then, how on earth do I compute the limit of this junk? And furthermore, I just don't want to compute the limit of this junk. Even if I were even if I were able to figure out how to do it, I don't want to. That sounds awful. There's got to be a better way. And there is, right? And that's what we're going to do now. We're going to take this formula here and we're going to turn it into something actually workable. Okay? And sort of the key insight here is that this seems an awful lot like an integration problem, right? Like if you think back to Calculus 2, when you first learned about the definite integral, like the setup of the problem there was you wanted to compute some area, okay? And it was an area of a curvy region. It was the area under the graph of a function f, okay? And what did you do? You said, I don't know how to compute the area of curvy regions. I'm going to approximate it by rectangles, because rectangles are nice. I know how to compute their areas. Okay, so you sort of chopped up the interval from a to b into a bunch of subintervals. Oh, that's exactly what we did. Okay, and then you say, okay, I'm going to compute the area of a rectangle on each of these subintervals and then add them up and then take the limit as the subintervals have width going to 0. That's exactly what we're doing here, right? Like this is a limit of a sum of some function. This screams Riemann sum, so therefore it's screaming this should be a definite integral. Okay, and it turns out that it is. We just have some minor details that we've got to work out to sort of put it in that formalism, okay, to really show that it actually is a definite integral. But that's the idea. Okay, it feels very integration-y. Okay, so how am I going to do this? How am I going to turn this into a definite integral? And here's the trick. What I'm going to use is I'm going to use a theorem from first year calculus called the mean value theorem. Okay. And sort of the reason for doing this is if I look back at this horrendous limit of a sum here, if I want this to be a definite integral, I need something that's going to play the role of like the dt on the sort of far right hand side of the definite integral, right? I need something that's playing the role of the infinitesimal that sort of the integral is being taken with respect to. In other words, I want to get a delta ti over here, in this function that I'm summing up and taking the limit of. And the mean value theorem is going to let me do that. Okay, so here's what the mean value theorem says, just to remind you. It says that, okay, if you focus on any one of the coordinate functions, so any fj, one of the coordinates, the jth coordinate of this path that we're dealing with, okay, if that coordinate is differentiable, then one thing I can conclude from that is that in each of these subintervals, in each interval from ti minus 1 to ti, there's got to be some point where if I plug that point into the derivative, I get this ratio here. I get the change in the output values divided by the change in the input values. In other words, I get fj of ti minus fj of ti minus 1 divided by ti minus ti minus 1, right? That's what these deltas mean. It just means the change over the interval. Right? And if you haven't seen the mean value theorem before, or if you've forgotten what it said, like all this is saying is that, well, like this quantity over here on the right, this is the average rate of change of the function fj over this entire interval, right? If you were to plot this, what's happening is this function fj is doing a curvy thing on that interval. And if you just connect the rightmost and leftmost endpoints, then that straight line slope right there, well, that's just what this is, right? Like it's rise over run. That's all this ratio is here. It's rise over run on that interval from ti minus 1 to ti. Okay, and what the theorem's saying is, okay, great, if that's the average rate of change on that interval, then, well, there's got to be some point in the interval where that average rate of change is actually equal to the instantaneous rate of change. Okay, and that's the trick that we're going to use. Okay, this tij tilde, okay, this, I mean, that's just the name that I'm giving to this particular point, and I don't know how to find it. Okay, but that's not the point. I just need to know that, yeah, it exists. Okay, so what I'm going to do is I'm going to take this mean value theorem statement right here. I'm just going to rearrange it. Again, remember I want something multiplied by delta ti? So I'm just going to do that. I'm going to multiply both sides by delta ti here so that, now I've just got this thing, delta fj of ti equals this thing times delta ti. Okay, so I just rearrange it, bring the delta ti up by multiplying both sides by it. Okay, and now what I'm going to do is I'm going to take this formula here, delta fj ti, I've got a formula for that, and I'm going to plug it in to each of these slots in our arc length formula from earlier. Okay, and when I do that, what do I get? Okay, well, the arc length of a path, it just by definition, this is just copy and paste from earlier, it equals this horrific expression, but now I can replace each of these by this formula up here. And I mean, at first that doesn't seem like it's going to get us anything much nicer, but it is a little bit nicer because this delta ti that's in each of these brackets, I can pull it outside. Each of them is squared, but then also each of them is square rooted. So I can just pull a delta ti outside of the square root, and I get that on the outside there. Okay, so this, it's now another new formula for the arc length of a path. And I mean, in some sense, it's a worse formula because, like I said, I don't know how to compute these values. I don't know how to compute tilde ti1, tilde ti2, all the way up to tilde tin. Those are numbers that I know, hey, they're in these small subintervals, but I don't know how to compute them. So, like, for practical purposes, this formula here is useless. Okay, but what I want to do now is I want to look at this formula and I want to compare it for the general form of a Riemann integral. Okay, remember, how is a Riemann integral defined? It was, okay, if I want to integrate some function g of t from a to b, okay, in other words, I want to compute the area under the graph of this function g from t equals a to t equals b, then what it is it's the limit of delta ti is going to 0. Okay, so these partitions, these subinterval widths are going to 0, and then you add up on each of those subintervals, the height of the rectangle times the width of the rectangle. Okay, and by definition, like, this is what a Riemann sum is. This is one way of defining the definite integral. Okay. And well, this thing here looks a heck of a lot like this thing down here, right? Like this thing up here looks like a Riemann sum. It looks like the Riemann sum definition of a definite integral. Okay, so I would like to pin that down. The only thing that I've got to do is figure out, okay, well, what is the g? Like in this thing here, what is the function g? And here's a choice that almost works. Okay, it doesn't quite work, but it's really, really close, right? Like it looks like I want to pick g of t to be this thing here. Okay, it's f1 prime at t squared plus f2 prime at t squared all the way up to plus fn prime at t squared, and then all square rooted. In other words, it's the length of the vector f prime. It's the length of the velocity vector. It's the speed. I really want to choose this g, this as my function g, because then if I plug that in over here, what do I get? Well, I get exactly this crap with one minor problem, and that problem is I don't get ti1 tilde here. I get just a ti tilde in this slot. And similarly, in the next term in the sum, I'm not going to get ti2 tilde. I'm just going to get another ti tilde. And over here, I don't get tin tilde. I get ti tilde. In other words, like if I do this thing here, okay, unfortunately, I'm only allowed to choose one ti tilde for every single coordinate function, for f1 prime, for f2 prime, all the way up to fn prime. It can't depend on which coordinate function I'm plugging into, whereas in my formula for arc length, which ti tilde I'm using does depend on which coordinate function I'm plugging into. Am I plugging into the first coordinate or the nth coordinate or the seventh coordinate or what? Okay, so I need some trick to get around that one minor hurdle, and then I'll be done if I can figure that out. Okay, and we're admittedly going to gloss over this point for the most part, but sort of the idea is that if I make the extra restriction that each of the derivative functions, each fj prime, if I make the restriction that each of those is continuous, then there's actually no problem here, okay? And we're gonna, like I said, we're gonna gloss over the details of exactly why that is, but sort of the high level idea is if each of these coordinate functions, each of these f1 prime, f2 prime, all the way up to fn prime is continuous, then what that means is changing the input just a little bit will change the output just a little bit, and therefore shouldn't really have any effect on this limit here, okay? And well, remember, each of these ti1 tilde, ti2 tilde, all the way up to tin tilde, where are those coming from? Well, those are coming from the interval ti minus 1 to ti, and that interval, it's having its width squished down to 0. Okay, so even though, yeah, like there are n different ti tildes, right? Like really in the limit, like in the regime that we care about where the delta ti's are going to 0, these n different input points all have to be really, really close to each other, right? Because they're all in the same interval of super small width. And therefore, these f1 prime, f2 prime, all the way up to fn primes, those all have to be sort of really close to what they would be if we only plugged in one ti tilde as well. Okay, so that's kind of the high level idea here. And for that reason, we're gonna need that whenever we use this upcoming formula for computing the length of a path, sorry, the arc length of a path, we don't just assume that it has a derivative, we assume that it has a continuous derivative. Okay, so a little bit of a definition here. We're gonna say that a function is C1 if it has a continuous derivative. It's not just differentiable, but even after I take its derivative, those derivative entries are continuous functions as well. And that's a slightly stronger property. Okay, and in this notation here, yeah, like the C refers to continuity, the 1 refers to the fact that it's a first derivative I'm talking about here. We took the derivative once and we got a continuous function. You can also talk about like C2 functions or C3 functions, and that just means that, like, for example, you take the derivative twice and it's still continuous, or you take the derivative 3 times and it's still continuous. The 1 is just how many times did you take the derivative while preserving continuity. Okay, so anyway, what happens when we throw all of this together? Okay, well, I said that we can basically choose g of t to be the speed function here, and then what happens is our arc length formula boils down to the definite integral. Okay, so that's what our formula is. Okay, the arc length of a path, what is it? Well, for a C1 path, a function that has, where you take the derivative of any of its entries and you still get a continuous function, well, then its arc length, it's just the definite integral of the speed of that path, of the length of its velocity vector. You just integrate that and you get your answer. Okay. And there are a couple of nice ways to think about this. We already mentioned actually some ways of thinking about this, but we didn't really justify it back in lecture two. Okay. One way to think about this is okay, yeah, the arc length, it's the integral of the speed, which sort of like that kind of makes sense depending on your level of intuition with definite integrals, right? That means like sort of if you integrate just a little bit more, like how quickly is that going up? Well, by the amount, like how quick is the particle moving? That's the same thing. Maybe let's flip this around. I find it a little bit easier to think about this if we flip it around a little bit and think about it in terms of derivatives. Remember, fundamental theorem of calculus says, okay, if arc length is the integral of speed, then that means that speed is the derivative of arc length, okay? And how you can think about this is like the derivative of arc length is speed. In other words, like what's the rate of change of arc length? Well, it's how quickly the particle is moving. And that makes sense, right? Like if you imagine a particle moving and you construct a function that measures, okay, how far has the particle moved? And then you say, okay, how quickly is that function changing? Like what's its derivative? Well, that's the speed of the particle. Okay, and that's all this theorem here is saying. Yeah, derivative of arc length so far, that's speed. So therefore, arc length is the integral of speed. Okay, anyway, let's do a couple numerical examples and then we'll be done. All right, so suppose, r is bigger than or equal to, sorry, r is bigger than 0. And, well, let's compute the arc length of the path that goes from 0 to pi to r squared. It's defined by r times cos t, r times sine t. Okay, so we know the answer to this before we even do the computation, right? This here, this is a parameterization of the circle of radius r. So what is its arc length? Well, it's just, how far around is the perimeter or circumference or whatever you want to call it. It had better be 2 pi r if I believe that this formula is any good whatsoever. Let's double check that. Okay, so first off, velocity vector, just take the derivative of each of the entries. R cos t becomes negative r sine t. R sine t becomes r cos t when I take the derivative. Okay, next up, compute the length of that. In other words, compute the speed of this path. So you just square it, sum them up, square root, and remember that sine squared plus cos squared is 1. So this thing here just reduces down to the square root of r squared, which is just r. Again, remember r is positive here, so I don't need to worry about absolute values or anything like that. Okay, so the speed of this path is constant, okay? The particle, it's moving at like r meters per second or whatever the heck the units are, okay? No matter where it is, it doesn't depend on t. All right, next up, how do we get the arc length? Well, I just take this speed that I computed, and now I integrate it over the domain. Okay, so I'm going to take this speed right here, and I'm going to integrate it over the domain, in other words, from 0 to 2 pi. Okay, so I integrate r from 0 to 2 pi, and when I do that, I mean, the integral of r with respect to t is just r times t, and then I plug in 2 pi, I plug in 0, I subtract, I get 2 pi r exactly like I expected, okay? I get the perimeter or circumference of the circle of radius r. All right, let's do a sort of a less straightforward example, an example where sort of we don't know the answer ahead of time, okay? And maybe let's go to a higher dimensional example as well, because maybe we're too comfortable with things in R2. Let's go to a weirder sort of situation. Okay, so let's compute the arc length of the path. This time it's going from 0 to R3, so the domain, the t values are going from 0 to 2, so that's where we're going to be integrating from 0 to 2. Okay, but the output this time is in three-dimensional space, okay? And this curve, I mean, you don't need to know this, but the curve looks something like this. It's just like, it's a piece of string floating in three-dimensional space. We want to know how long that piece of string is. All right, so how do we do this? Well, step one, velocity vector. Step two, length of that velocity vector. In other words, norm of that velocity vector, throw bars around it, sum of squares, square root, that whole thing. Okay, so velocity vector, take the derivative of each entry, t becomes a 1, t squared over root 2 becomes root 2t, and t cubed over 3 becomes t squared. And now length of that vector, so square root of sum of squares of entries, so t squared, squared, etc. for all the other ones, and you just compute that thing, and if I expand all this crap out, I get this here, and something really nice happens here, and that is, well, this 1 plus 2t squared plus t to the power 4, I recognize that as just 1 plus t squared all squared, right? This here, this 2t squared, that's the cross term if I square 1 and a t squared, okay? So I can factor this thing inside here as 1 plus t squared all squared. And that's really nice because now when I take the square root of it, this outer square just cleanly goes away, and I find that the speed of the particle, or the speed of the path, is just 1 plus t squared here. Okay, so not too bad. Now, to compute the arc length, what have I got to do? Well, I have to integrate that, right? You integrate the speed over the domain. So from 0 to 2, t is going from 0 to 2, integrating the speed. Okay, and that's not too bad of an integral, right? When I integrate that, 1 becomes a t squared becomes a t cubed over 3. Plug in your endpoints, t is going from 0 to 2. I'm just going to get 2 plus 2 cubed over 3, so 8 over 3, and simplify that a little bit. It's 14 thirds, so that's the length of that path, or the curve traced out by the path. Same thing. Alrighty, and yeah, just to sort of clarify that point a little bit before we leave, really, like, in this video I've been talking about the arc length of a path, but really, like, it's a property of the curve that the path traces out. We're gonna flip back and forth between thinking of these two things, okay? I'm gonna sometimes think of, like, the curve as having already been traced out. It's just a static piece of string in space, and I want to know how long is it. That's a fine thing to do. I can talk about the arc length of the curve. But also, like, sometimes it is useful to think of, like, the arc length of the path, which is like how far has the particle traveled so far. Okay, so I am going to sort of abuse terminology a little bit and talk about both the arc length of a path and the arc length of a curve, which without worrying about the distinction too much. All right, that's all I've got for you today. Thanks for watching, everyone. I'll see you next time.